Hello, my name is Eyal Ofek. I'm a principal researcher in Microsoft Research Lab in Redmond. My main interests are virtual reality, augmented reality, and haptics. And today I will talk about using virtual reality and augmented reality as a place to do work when you're on the go. And let's go. So the concept of the office, as we know it, is changing. More people are working from home and locations far from the physical office or while on the move. This progress have accelerated with the COVID-19 pandemic and their resulting lockdowns. It introduced many positive effects, such as enable to work at flexible hours and reduce commute time, enable people that are far from the office location to work, and being more accessible for people with physical limitations. However, it also has limitations. People have to work in less than optimal workspace. They have limited display, for example, a laptop screen when you work on a train or in a makeshift office, rather than an arrangement of multiple video screen that you might have at work. It has less than optimal lighting. There's a problem of privacy and prying eyes all around you, disturbances, and in the later years, you see people working on a plurality of devices, from laptop to tablet to phone, and how we can leverage all of them for one workspace. Now, if we look on virtual reality, its technology has progressed by leap and bounds. We can now buy cheaper headsets that are aimed at consumer market. They're lighter. Their resolution is gradually growing. We can already buy headsets with resolution of about 2,000 by 2,000 pixels, which getting to the good monitors that people use for work. And they have inside-out tracking of the head using cameras that are mounting on the headsets, and those allow us to work everywhere, not just in rooms that were prepared for tracking. They allow us to track the hands as they move around, controllers, and they also allow to pass the video from outside inside the display without the need to take off the headsets. And much of the hype around VR been focused on immersive applications such as gaming and entertainment. And in this webinar, I'm trying to focus on the use of those VR headsets for productivity and how to overcome problems that I mentioned. We suggest a novel immersive workspace that will be, on one hand, use large display space, which is organized in a familiar manner. Oh, that looks like my office. It will have an optical lighting. It will protect whatever we work on from prying eyes, and will reduce distraction in a selective manner. Some people that are approach us, we want to get to know about their approach. However, we are doing something which is different than most VR applications, and we limit the user input space to a very small space. And there's a reason for that. If we look at applications that exist right now that let people move around the space, reach with their hand to virtual objects, which is very engaging, but when you are in a limited space, that might be a problem. Also, when you do large gestures such as reaching out and using hands in the air, this requires a lot of effort, and it's hard to do such a work for a long time. After most VR applications, after 15, 30 minutes, we are already quite exhausted. So by using small motions that are mostly supported by our devices, by desk, we enable to let the user work for longer hours and use their gestures and muscle memory even when the environment changes, but we want them to be able to control a large display space around them. So let's look at different tasks that we need to do for the information worker. Let's start with a very basic one, typing. How do we type in virtual reality? Usually, as applications looks at people that are standing, moving, they tend to use large keyboards that you point on them with controllers or with hands, but you use large displacement of the hands to minimize typing mistakes. Well, this is good for a moving user. It mostly aims at sporadic short input sequences rather than full editing of a document. We need to change our thinking of a design from large energetic motions to sitting with good posture and ergonomics, where our gestures and hands are supported, and which allows us to do very delicate selections and for a long period. So if we think about sitting people and entering text, by far the most common way to enter text is using a QWERTY keyboard, which although they're not necessarily the best, or haven't changed in the last century and a half, mostly due to the familiarity of people with them. And we want to leverage on that familiarity and the haptic feedback that we do get from a physical keyboard and continue to enjoy that also in virtual reality. However, in virtual reality, we put a head-mounted display on our head, and as such, we block the view of the hands and the keyboards from the user. So some users know touch typing well, and they can continue typing just by looking at the documents, but we want everybody to be able to use the keyboard. One option is to allow visibility of the keyboard and the hand by cutting the part of the display. Some of the display will be the document, and some we can look down, glance, and see our hands. While reducing the immersivity of the experience, it's also doesn't let us do different effects that we will talk about later when we are working in a virtual world. So, but this is a legitimate way to go. Just as well as using the cameras on the headset to stream video of our hands and keyboard in real time to the user. And finally, we can use those cameras and computer vision to track the hands, track the keyboard, track the devices, and display them as virtual objects in the virtual space. Already, existing devices such from HoloLens to Oculus Quest to HTC Vive Pro enables such tracking in real time. And we can also use for our benefit the fact that the keyboard has a fixed view, or we can use the display of the devices, which we don't see because of the head-mounted display, to show different information that can help the tracking. So in this case, we need to display the keyboards, display the hand, display the working environment in virtual reality. Is what will be the best? We just talked about different ways of doing so, and usually the way that we could check that is via studies. So let's start about what will be the best way to represent our hands when we're typing. We mentioned four options. One was don't show the hands at all. Maybe just as a touch typist, just show which keys are being pressed and the update of the document. We can just as well show a real-time video of the hands. We can model the hands as fully fleshed 3D models that type on a virtual keyboard, or maybe something totally different. For example, show the tips of the fingertips as if our hands are transparent and we can see the keyboard through them. What would people will prefer? So when you give participants a chance to type text in those modes, we can see several things. One is that the speed of typing almost never change regardless of the mode, but the quality of typing, the number of errors that people do change. And while we expected video to be a very good representation, as close as possible to real life, it's surprising to see that just rendering the fingertips is almost as good. Another surprise is that when you give a full model of the hands, we found out the number of errors increases almost the same as not showing the hand at all. What's happening there? It might be due to small differences in the tracking and the uncanny effect, which people look at the hand and say, that's not my hand, it's artificial hand. And although they do type, it has some lowering of quality. When asked people what do they like, they mostly like the video because that's closest to real life. But again, surprising enough, the fingertips are not far behind. What about the position of where our hands and keyboards? When we look at people typing in VR, we see that they have less than perfect pose when they type, and there's a reason for that. When you look through head-mounted display, you notice that displays have a limited vertical field of view, which many times you cannot see both the hand and the keyboard, which are on the table, and the document you edit, which many times is in front of you. To make things worse, we actually, if we look at the lenses that those head-mounted display use, they're not perfect either, and they are non-uniform. They're much worse next to the edges of the display, which lowers the practical field of view in which you can read text even further. So wouldn't it be nice if we could take the hands and keyboard, which may be rendered as a virtual object, and just move them close to where the document is being typed and away from where their physical hands are? Would that disturb the users? So that's exactly what we did. We moved the keyboard and the hand and we target them to be close to the user's view direction. And as you can see, the pose is immediately become better. What about typing? So when we look at that, surprisingly enough, if we look at physical keyboards, the yellow ones on the top, there is basically same performance, whether the keyboards are where they physically are or if we show them floating in the air where the user is looking at. Regarding touch keyboard, there is some reduction in performance, and that's probably to the fact that we need to disconnect our fingers from the glass and then reconnect, and then that movement in the air is more susceptible to a change of orientation as big as 3 degrees as we used in this experiment. However, regardless of what the keyboard is, there is a great improvement in head pitch, which is mostly looking forward and not down as it used to be before. What about the keyboard itself? We talked about how we may render the hands differently, but we can also change how the keyboard looks like. And you can see that in real life in specialized keyboards, such as gamer keyboards, keyboards that has shortcuts on them, such in control rooms. Here we have a virtual keyboard display. We can actually change it every minute according to the need. So when we come to look at possibility of changing keyboard, we can distinguish of two axes of design. The first one is how we interpret the use of a click on a keyboard. The first option is what we familiar with in real world. When we click on a button in the keyboard, it's regarded as one press of one key. But since you might not see the keyboard as it is, we can actually have different type of inputs. For example, we could have multiple group of keys just behave as if it's one big key. And no matter where we press in it, what the system will get is that key input. And we can go with that even further. Let's assume the whole keyboard is one key. What's the information that we get there? We assume the keyboard as if it's a touch screen, or it has an X and Y axes, and what we care about is where the user is actually putting its finger. And in fact, we could even have a higher resolution than the keys if we look at multiple key presses and see that the user actually pressed in between keys. So that's input. Let's talk about the display or the output. The most common way is the graphics that each key has on it. We can change that according to applications. For example, you can think of applications such as lowercase, uppercase, different languages, and different languages not just per key. For example, here when we type in German, every character might have other ways of writing it with additional marks. So as you type, you actually show the different variation of each character, so you could have another click to change that view. Now, usually this is not very efficient because the user has to break out from the document and look down on the keyboard. But again, in our case, we can bring the keyboard just where the user is typing and show the options with the finger and that, which makes it more efficient. We can use application shortcuts, jumping alt tab to different applications, tabs on the browser, and ways that are changing according to the current arrangement that we have on the screen. We don't have to remember them in our head. Also, we can use that to enable better privacy. For example, I'm, say, working on a plane and I want to type in passwords. I don't want to reveal that to people around me. And we could change the mapping between the keys and their semantics. And there's a range of options here that has a trade-off between more shuffle and security to easier, faster typing according to the need. But we can change more than just the graphics on each key. We can start changing the keys themselves because the user does not see the keyboard. So we can have bigger keys if we want for stronger semantic action. For example, one space movement, two entries movement, or jump to the end of the line could have different size of keys. And this could change according to our needs. For example, here we have a window manager where we press Alt-Tab and we see what applications are there, and then we can immediately jump to an application by pressing the button. Now, the less number of applications, we can have bigger buttons, so it will be less effort to select them. We can also change the size of the application according to the view direction of the user, which we get from the head-mounted display, so that applications which are probably the user looks at will appear bigger and easier to select. We can use that to browse different medias. And again, we show here, use the resolution of the keyboard for selection, and obviously you can have multiple keyboard layouts and page between them. And maybe the most interesting is how can we break the mold of the keyboard and use it in a totally different way. For example, maybe ignore the rest of the keyboard and just look at the functionality that we need. And to demonstrate that, you can see, for example, here access to a timeline of a video by using the upper row of digits. Now, although it looks like there's 10 selections there within position of the video, you can actually press in between keys and have more selectivity over there. Now, you only need that line. What if we'll only show the line to the user, not the full keyboard? It does help people to focus on that task, but on the other hand can generate accidents because you might hit parts of the keyboard that you're not aware of. So representations such as the top left, where you are focusing on the keys but also aware that there is a mass around it that you should aware not to hit, might be better for such uses. So we can take those two axes and generate a design space where different application might be use different inputs and different outputs. For example, the one on the top right is our implementation of a whack-a-mole game where the whole keyboard is just one key and it sends where the hand or the hammer touches it. What about the screen? When we work on a tablet, we use a 2D screen, which is our entire display space, our entire input space. Maybe I'm, again, sitting on an airplane and put my tablet on the tray and work. And on one hand, it's great. My hand is supported by the tablet. I'm not getting tired, but it has very limited input space and display. So we can use the fact that we have wearing a head-mounted display to enrich this environment. For start, we can look at the space above the tablet. Although the hand is lying on the glass, it could still tilt the stylus up and reach higher points in that space, which, for example, we can use to generate different layers of different semantics at different heights. And of course, we can increase to a vast display space all around the tablet, to our right, to our left, and in front of us. So how can we use that? And there's different designs that we can go. I'm just suggesting one design here that we were looking at, in which you have the tablet, and we could use the space above the tablet for different semantics layers, versions, remarks, a inner working of the application. We can use a larger space for our interaction a bit, where we actually move the physical screen mapping to that bigger screen, virtual screen, so that we can use a bigger input space. And we could use the display space around us to show different views of the data, different tabs, different spreadsheets that we can reach out and use, as well as overviews in front of us that enable us fast access and detection of changes. So let's take an example of a spreadsheet, such as Excel. Right now, we are working on the tablet, and when we use our depth information, we can see things which are behind the tablet. The tablet display is very simple. It's a regular grid of data, which is part of its attractivity and simplicity and easy to learn. But it's harder to see how a function is built up or how the data flows in debugging, or even if you have figures and you want to change the sources for it. By enabling additional semantic layers and having nodes in those, we can easily make manipulations and modifications or debugging. Also, it enables us to get help where we need it. For example, if we need a menu here, we don't need to go to the edge of the view. We can tilt the stylus up and reach that menu at different levels. We can generate nodes that summarize ranges in the spreadsheet and have those clustered display easy to copy and use for different applications. And And finally, we are tracking our hands, both the dominant hand with the stylus, a non-dominant hand might touch the screen just as well. We have our head moving, wearing a head-mounted display. We can even have eye gaze. And by doing that, we can quickly jump around and map our limited input space to different parts of the data so that we could have very fast and efficient way to work. Up till now, I was describing the work as a standalone. I go to some space and I unpack a virtual office around me. However, different spaces look different. They might have obstacles, bigger, smaller. They might have other people, and the application should be aware of that because it could affect the way we work. So if I want to go on an airplane and just unpack my multi-screen environment and be able to work, I might ignore the fact that I may be in an environment that a coworker might come and talk to me, the stewardess in the airplane might come and ask me questions, and I also want to use affordances in the environment. For example, I want, if I draw, that it will be on some supporting surface and not arbitrarily in space. So we need the applications to be aware. Even more than that, what we want is a magical application that we write once, but then it can run differently in different spaces according to their affordances. So we developed a system called Flare, fast layout for augmented reality experiences, that is using learned rules or predetermined rules to lay out the workspace or a game, for that matter, in the environment, regardless of whatever the environment shape is, and balance between the limitation of the environment and the need of the user or the game. So I could, for example, go to my office or my preferred environment and just plan how things gonna be. My contact's gonna be on my right, and updates gonna be on the left, and the main document in the center, and so on. And then pack virtually everything, and whenever I go to some place, it will unpack in a way that will be both familiar to me. I expect the contact to be on my right, but also fit the environment. So to do that, we look at the environment, whether it is using color cameras, such as on the head-mounted display, or depth cameras, as HoloLens have them, or maybe using the motion of the color cameras to generate reconstruction of the environment on the fly. And then by analyzing it, find out for semantics affordances in the scenes, walls or places that will be great to put displays on, tables and places that could be work surfaces, areas where people are walking around, maybe you want to avoid that, and so on. And for augmented reality applications where we do see the real world, we also look at the silency, which is a measure of busyness of the world around you. Maybe we don't want to put a virtual monitor where there is already a monitor that we need to see or signs. And giving that as an input to the system, as well as our preference for the work or the needs of the game, we can adapt for each environment. So for each room, for example, the game on the left looks different, but it's playable. And it still obeys all the rules of the game. Now, not just monitors and input spaces, also collaborators may be represented in our space around us, and this representation should be updated as the environment changes. For example, someone gets into the scene. In this system, which is a projection-based system, you can see that the collaborator is mapped to a chair, but when that chair is taken, we map it to a different chair. It could be that these had to be done in parallel for multiple users and their displays. Another issue that we're dealing with is privacy, and in this time, not privacy from prying eyes around the user, but the actual developers of the applications. The more applications know and being mapped to the environment, they potentially knows about the user, and we don't want that. We would like to generate a sandbox by the local operating system so that an application may come in and describe its need. These and these displays, they need to be accessible for the user, these and these surfaces for input, and as the operating system accumulates demand from multiple applications, it could assign them accordingly without having any information leaks back to the application. And very super important subject for us is enabling accessibility to people who might have difficulties to use them. At this point in virtual reality and augmented reality use, it's mostly looking at getting the market big and less fitted for special needs, and which we try to look at it. For example, here you see a video of simulating how a person with low vision will see a virtual reality application. Now, according to the World Health Organization, in 2018, there were more than 217 million people worldwide with low vision. And by low vision, I mean that glasses or lenses cannot correct the limitation. It could be a variety of effects such as blurriness, limited field of view, tunnel vision, spots in the field of view that you don't see, sensitivity to light, lack of sensing depth or assessing distances, and so on. So to enable both users to use applications that exist as well as developer to easily apply uh, solutions for the user, um, we developed a toolkit called Seeing VR, which stretches from simple tools such as an automatic zooming when you look at an object to segmentation of objects and show better way to separate between them where one starts and the other end, to enhancement of text, to readout of text, and all that is being shipped out as an open source toolkit, which you can find in this address, as well as in other publications and project pages that we will share at the end of the webinar. So I just want to thank, of course, such work was not done by a single person, done by a lot of people, where researchers from Microsoft Research currently and in the past, professors from other universities that collaborated with us, students, and research interns, which all worked hard on those projects. So where can we take the technology further? I mean, this is a very short webinar and cannot cover all the work that we did or work that can be done in this area. We are very excited about the fact that this combination of smart systems that are aware of the user needs, as well as the changing environments around the user, and could change the work environment accordingly, can give us. We also think that this virtual space can enable people to do things that they couldn't do in the real world, or level the playing field for people with physical limitations. For example, the images that you see on the right are from a work where a person is walking in the Microsoft campus, and the system show him as if he's in a remote site, in this case in lower Manhattan, but it could be in a different lab in Europe. And while the system is aware of obstacles and people around it and make sure that he walks safely, it also should be a bridge between his physical environment and the environment of the remote site that he visited. And technologies like I showed and this, we hope that will open up jobs for people that live remotely from the offices, that has a problem to access the offices, maybe lower needs for transportation, can reduce the jump or the ramp up that we need to go when we go from one task to another, control external disturbances, and more. So to summarize, we hope that the freedom of the mixed reality, along with better sensing, will be a fertile ground for further research that will change the way that we work in the future. And we sure hope that when we maybe talk about that in a few years to the future, we'll be surprised of what we actually saw. And by this, I will go end up this webinar and open for questions. Thank you all. And I will refer you to our link page for additional content. Thanks.
Hi, everyone. Thanks for attending the Enhancing Mobile Work and Productivity with Virtual Reality webinar. And now we're in the live Q&A session. I'm Eyal Ofek, and over the next 15 minutes, give or take, we're going to be answering top questions submitted by the audience. So let's get started. Let me look at the questions. Okay, so the first question that I get, is how much of my work do I do in VR and MR? And that's a good question because we are still in a process of getting the HMDs to be good enough for work. There are several issues that need to be dealt in order to really be able to work for long hours in HMDs. One is the quality of the lenses, which right now are quite low because it's aimed at entertainment mostly, but if you're buying it for work and you think of it as a large 4K display, then you might be able to invest more in the HMDs. And you can see in HMDs such as above $1,500, you start to get really good lenses. Second is you need a resolution for the text, which we are getting there if we're looking at the HMDs, commercial HMDs like the HP ones. And obviously we want it to be light. Now, given that, I do quite a lot in VR because that's my work. And if I go in a situation such as travel, then I think it's a no-brainer. It gives me a very private and expensive display that I could use when working. How would VR help someone with glaucoma? In general, you can think of an HMD as a private display that is close to the eye, and mostly, although the eyeball is rotating, it's closer to the eye coordinate system than, say, an external displays. And that could give us different things that can help people with vision problems, such as limiting the display into a small part of the field of view, which is better for people. And it could sharpen information. It could add additional cues to highlight things that you might look at. And the HMD gives us a rough view direction that people look at. So if you will look at the work of the Seeing VR, you will see a different slew of techniques that can help people. I don't know if that's specific to glaucoma, but it does range a different kind of artifacts. What would be the perceptual implication of foveated display? Perceptual. I'm not sure. Can you send a bit more detail in your question? There was, let me see, more questions coming in. Okay, so again, you have to, there's an ask questions about how to use handle damage by head-mounted glasses, which I think I said something, and also neck injury. We did the specific work on that, where you think of an HMD or VR as a mean to mediate the visual input for the user. So We could do things such as limited head rotation, maybe if we know that a certain direction is problematic, we can try to arrange information in a way that will limit that rotation. Okay. Regarding the question, is it's great to see that you're looking into accessibility in XR early on. Is there a goal from MSR to enable XR as an accessibility early on, or is it more an opportunistic basis? No, it's actually, we do try to incorporate accessibility into many things we do starting on. And there's, we work in coordination with their specific accessibility teams, both for Windows and Office, and MR that tries to work on that. Is it possible to skip the traditional input devices for computing for VR, like recreating keyboards and just jump into speech or brain interface control? Potentially, but you could say this is not necessarily a VR question. Is there potential to go beyond the mouse and keyboard in general for typing? And up till now, it was really hard to do. Speech has a problem of privacy as well as annoying people around you, while brain interface might be a good thing. I don't think it's right now as accurate as you would like it to be for sort of brain typing. And let's see. It seems though as HoloLens would support more enhanced virtual productive environments based on being able to maintain awareness of the natural environment. Is MS working on more productivity applications for HoloLens 2? Yes, for sure. MS is working on more productivity application for that. Regarding the environment awareness, this is quite a high level awareness in which you could script out different behaviors that you could see between the either the AR display or even VR and what's happening in your environment. This currently is not in the main direction of HoloLens, which looking at the field workers and specific tasks, but it might be. Can VR projects be afforded by people financially challenged? Are VR projects costly? Right now, it's emerging technology. It might be costlier than it should be, but I clearly see how HMDs are becoming a commodity. You can already buy quite good ones, such as the Oculus Quest 2 for $300 or maybe even less. And I can clearly see how it will go lower than that. And if you are trying to compare them to equivalent displays that you need to buy to get you a large working environment, I think they're already getting there to be competitive in price. How developers can use VR, for example, IDE like Visual Studio. Right now, there's several standards of VR that's coming out, like OpenVR, OpenXR. Microsoft has a standard for MR, which tries as much as possible to remove the load from developers and enables you to do easy development there. And yes, within Visual Studio too. Prolonged psychological impact on human mind to incident of a non-physical world. We haven't done really long I mean, we mostly looking at the content of a workday, and I must say that there's a obviously effect such as people looking at screens all day long. It's a bit better, by the way, from screen because it does react to what you do and movement. And they try as much as possible to make the head-up display as close to your natural display. In particular for AR, I don't think there is any significant effects there. Let me look at questions that already has the COVID pandemic impacted the XR industry in your opinion? Well, it affected every industry, I would say. For XR industry, it's plus and minus. Obviously, development is harder at that time, and especially when you want to do user studies and you cannot meet your participants, you have to send them hardware. It's harder, but on the other hand, it gives more focus on the need for better communication and better getting out of your current environment, which is a boost for this area. Okay, let's see. Was a question about meeting rooms in a VR sense, and that will be interesting because I believe there will be more people calling from afar, as well as there's a mix between people in the same room as well as people outside. And what we do think and try to do is to make people that call from outside, which right now do suffer from the fact that they don't have a physical instance in the meeting room. They're just voice from afar that's hard to get in. They don't hear well for the other participants. They don't have what we call a reference space, which is between the body of the participants and, say, a task or a document. They cannot point or give other movement gestures, and we hope that VR AR can help us on this sense. Can VR projects be integrated with robotics or HCI? Of course they can, and people actually do that. Whether it is that you put yourself as guiding off a robot or that you represent your physical being in the remote space by a robot, this is something that we did work on. Okay. What is your view on the key driver to make work in VR ubiquitous? Do you think holoprotection could play a big role or even be a key driver, especially now that people have a hard time to meet physically? Yes. I mean, I mentioned that before, but in general, when we look at VR or AR, it's a way to mediate our sensing. We right now mostly mediate our visual and audio. We are working hard also on haptics. You can see that in my webpage. And the target for that is to modify the environment around the user to better fit the task that she needs to do. So if the task is right now to collaborate with other people, then we are looking at ways that this could be enhanced with VR, such as representing people gaze and body gestures that can help working together. There is a funny issue of HMDs that when people wear them, they actually block their facial view and expression, which is important. But this is also being worked out in two different ways. One is making the display small, light, and transparent as possible, like regular glasses, so you actually see your collaborators. On the other hand is machine learning based reconstruction of the face from internal sensors. In terms of those prototypes for typing the keyboards and hands precisely, I saw it still use the optical motion tracking solution. Are there any prototypes that can achieve that high accuracy using via using only cameras on the HMD? So in the example that you saw in the video, as well as in HoloLens or Oculus, they use the cameras, only the cameras on the HMD, nothing else. Okay. A lot of questions on accessibility, which is great. Do you know if VR project intend to help people with disabilities or blind people? Yes. We did work several things for blind people, whether it is generating an haptic a cane that people can walk within a virtual environment, and they actually hear the audio from tapping the cane on object, whatever material it is or where it is from, and we show that people can actually go through a virtual environment, for example, in a game, looking for treasures much faster when they do that. Sorry. We also looking at people with disabilities and how we can use modification of their emotions to let them in the virtual world, which is non-physical, behave without any physical limitations. Question. Any movement towards smaller glasses? Yes, there are. I'm not developing HMD hardware, but we do see that from almost any major company, as well as small ones. While you work in VR, how do you get notification when your office mate wants to talk to you? So we are, and that we use both cameras that are on the HMD as well. And here I go beyond what I displayed here, which mostly was just using the off-the-shelf HMD as well as the laptop. And I could use both the laptop camera as well as other sensors that we can put on an HMD, like depth cameras. And those can give the system full knowledge about what's happening around. Where are people walking? Is the person coming closer to the user, or his face is facing the user, and do they talk? And when that happens, we way before before they start talking, we want to start to present them in the VR world so it will not generate any surprise to a VR person that suddenly he hears an audio coming from outside. So the more you are affecting the application based on what's happening outside, the less need users have to remove their headset and can just continue working. We even look at a more immersive applications such as games and how to incorporate real-world interactions into the game without with letting the person be safe and attentive to the world, but not breaking immersion. Do you have done VR projects for autistic and special children? I myself have not, but other people are working on that. So I cannot really tell a lot about that. How does 5G introduction change the current VR interaction in multi-space location? Very, very good question. It will have major change in several issues. One is the ability to transfer more information from faraway sites into the user, and very important, lower latency as you do that, so you can actually feel as if you are in a faraway space. So we are running out of time. Let's see if there's any other quick question I could answer. The next step beyond office productivity is the future work toward virtual laboratory productivity. So we didn't look specifically of laboratory, but if the issue is getting physical objects, moving them for different places, do operations, yes, for sure we do. There's a very large research effort that you can see on my webpage that is related to haptics and how we could actually feel that we're manipulating objects far away and have as much tactile rendering to do so. So I'll refer you to that. And with this, I will thank you all for attending today. We appreciate your participation and interest. And if you're interested to learn more, and we listed some great resources in the resource list. You can find them right to your screen. The list includes our published papers that relate to this. You can find more papers in our personal web pages, links to project pages, and also a link to the Seeing VR Toolkit. I hope you all enjoy this webinar and have a great day. Thank you.